Hi everyone. This series of videos is going to walk you through an example on page 17 because that example is going to stand as a pretty solid template for which you can follow all of the other questions in today's assignment. So page 17 and page 18 actually just contain multiple iterations of the same problem over and over again, and that's why you can apply what you're going to see in question number 7 to virtually all of the examples that follow. It's also worth noting that many of the things I'm going to go over on page 17 here are exact duplicates of things I went over in the video covering page 14. So if you've watched that video somewhat recently, you're going to end up experiencing a lot of deja vu. And it may get to the point where if you're watching the videos, you may say to yourself, oh, I already knew this, she already explained this. And it may not be necessary to watch the video for everything that you'll see here, because you may already have figured this out using what already has come out of previous iterations of this type of problem. So just know that this entire playlist is super optional. They're all optional, but really this one is ultra optional, because if you already know how to do a lot of this stuff, this playlist isn't going to teach you anything that you haven't already known. It's basically just going to give you another version of a similar problem for you to practice, and I'll reinforce some of the ideas, but I'll probably be repeating myself a lot. If you go back to the videos from page 14, you can hear much more of the same idea with a little bit more depth, and I would recommend starting there if you haven't already. This video is meant to be a second example. So as you may recall from class, when we do something the first time, I tend to put a lot of detail and a lot of emphasis on every single little aspect of a problem. But the second time and the third time and the fourth time we do an example, I try to pick up the pace a bit. I try to get to the point, and I don't necessarily belabor some of the details the way I do when I first introduce a topic. That means that if you really need some context for why I'm doing anything I'm doing in this series of videos, you should probably go back to the previous playlist, the week 32 Tuesday playlist, and start there. That should give you some of the necessary foundations for which this material is based. Now, in question number 7, what I want to start with is the values of g of 2 and g of negative 2. Just like we had in the previous example on page 14, we have a situation where they're asking us about a function that they're not specifically giving us. They are giving us something about the g function, and I'll highlight that in pink here so you can at least see what we're supposed to be using. But we'll notice that as we go through the question, it's going to ask us about g. Notice in letter A, g of 2, g of negative 2, letter B, g prime and g double prime, letter C, g has horizontal tangent lines, minimum, maximum. In letter D, g has points of inflection. All of this analysis is supposed to happen on function g, and yet all they're actually giving us in terms of math to work with is a graph of f. And that's not a mistake. It's not a typo. It's not that it's supposed to be a graph of g and we just made a mistake somewhere. They're actually not directly giving us much info about g at all. They're telling us that g is an integral, but even then, they're hardly telling us enough information about the integral. So the key thing about these problems, something that you should know, is that this is where the second fundamental theorem attempts to tie together how to take an integral while using a graph to extract all the important info. Many of the key relationships between the integral and the graph were explained on page 14. So again, make sure that you have a solid foundation there. What I'm going to start with, though, for each question is just with what they're asking me. And then I'm going to ask myself in response, what are they giving me to work with here? We only have two things to work with, a g function and a graph of f. So it's limited what I can do, but that's almost for the best. If there aren't that many options for me to consider, that means I don't have to think too hard about some of my choices. For example, in letter A, it says find the value of g of 2. So g of 2 implies that 2 is the x coordinate, because that, of course, contextually is where the 2 usually goes. So if 2 is specifically supposed to be an input for the g function, I'm going to copy out the g function, and I'm going to put 2 where the letter x is. So that would be the integral from 1 to 2 of f of t dt. Now, of course, you'll notice that t is a dummy variable. T is not implied to be an input of 2, so that's why I left it as t. And those of us who have done these before know that the dummy variable is going to end up being essentially meaningless anyway. Now, in context, when I see an integral problem, I always have two interpretations that I have to sort of juggle, sort of toggle between. One way of interpreting an integral is as an antiderivative. The other way of interpreting an integral is as an area problem from 1 to 2. So I have to ask myself, given the context, given what they're giving me to work with, which interpretation, antiderivative or area, makes more sense here? Since they're giving me a picture of f, but only a picture, they're not actually giving me a function to work with, I can assume they probably don't mean antiderivative, because I can't really take an antiderivative if I don't know the actual algebra behind this function. So the only interpretation of this integral that makes sense is the area interpretation. They must be asking me, indirectly, to find an area from 1 to 2 on this picture. So I'm going to look at my picture, and I'm going to find the area from 1 to 2. They're specifying that I start at 1 and end at 2. So I'll just shade that in lightly so we can see that that's really just this tiny little triangle here. Now, unfortunately, there's not a great labeling system here, so I'll have to just do the best I can with limited info. But let's assume that that is indeed a triangle, and let's use the formula for a triangle, which is 1/2 base times height. The base of this triangle is going to be from 1 to 2, so that's positive 1, times the height of this triangle. Seems a bit harder to find. Like, how do I know exactly where this point is? I'll have to use a bit of logic. This is a linear function, this little piece here. So if to go from 1 to 3 takes me all the way to -1, and 2 is halfway there, then this height must be halfway down. So if the full way down is -1, halfway down must be -1/2. So in terms of my area then, I have a base of 1, I have a height of -1/2 divided by 2 because it's a triangle. So if I do that calculation, 1 times -1/2 divided by 2 would give me an area of -1/4. And again, that interpretation is all I really know right now about the integral. So I'm going to say that the value of g of 2, the integral from 1 to 2, is -1/2. They didn't give me much to work with, so I didn't have to do much in response. I really just had to find that area because that's all I had. Now, by the same logic, g of -2 must also kind of have the same setup. The integral is still from 1 to -2 as my new x value, f of t dt. Remember, f of t dt is just a placeholder at this point. It's referring to the graph of f, so I know area is a more logical interpretation, and that means I need to find an area now from 1 to -2. Notice that the 1 is the starting point because that was a fixed part of the original function they gave me. I'm starting at 1 because the function told me to start at 1, not just because I happened to pick that point. They'll always tell you where to start. That's never going to be something you have to guess about. So if I start at 1 and go towards -2, I have a couple of different shapes to factor in now. I have this semicircle, so I'll have to consider that whole piece. And I'll have this triangle looking shape that I'll have to find the area of as well. So let's start at 1 and just think about each piece as logically as we can. We'll start with the semicircle. The formula for a semicircle is half of that of a circle. So if I think logically, a circle is pi r squared. Half of that would be pi r squared over 2. Let's use that as kind of our baseline here. The radius of this semicircle would be 1. So 1 squared is 1 times pi is 1 pi divided by 2 would be pi over 2. So I know for sure that the area itself is pi over 2, but let's think about the sign of this real quick. If I was starting at 1 and heading towards the left, the base of this shape would be a negative value. And since the shape goes down, the height would also be a negative value. So base times height, negative times negative, ends up yielding a positive area of pi over 2. It's tricky to think about that in terms of circles because we know that logically it's not really like you're doing a base and a height when you're doing the formula. It's more symbolic than it is to be taken literally. Hopefully that's not confusing. Then, of course, we still need to factor in this triangle from -1 to -2. So if I think about this again as a geometric shape, a triangle would be my best bet. I have a base of -1 because I'm going to the left. I have a height of 3 divided by 2 because it's a triangle, which gives me an area of -3 over 2. And again, just to make sure we understand the significance of the negative here, we have a -1 for the base, but a +3 for the height because we went up. Hence the fact that a negative times a positive gives me a negative area. If at this point it helps to color code some things so that way you have a bit more logic to your labeling system, do that. Anything to keep your numbers a bit more organized is always a good idea. Some people end up highlighting and color coding their values, as you can see here. Some people do it on scratch paper so they have a little bit more room. Lots of variations in technique, of course, but ultimately we just want to keep straight what we need to find. So I'll go back to my original problem again just to make sure that I know what I'm looking for. I'm looking for g of -2, which was the area from 1 to -2, so I would need to add the pi over 2 from the semicircle and the -3/2 from the triangle. And since I can't really add those, they're not really like terms, I'll just call it pi over 2 minus 3/2. You can convert that to a decimal if you want to, but there's no need because you'll never be given credit for doing such a thing, so keep it simple. Make things as easy as you can. Take some time to make sure that makes sense. Take some time to make sure that we understand why the area is what it is, because in the next video we'll talk about letter B. Again, if you feel like you see where this is going, you may not necessarily need these videos, so just use your best discretion. And as always, if you have a question, consult the answer key first to see if that confirms where you might be going with it. And if so, capitalize on your instincts that you already have to try to do as many of these without having to depend on the watching part.